Yes, I've been asked to comment. I'm not going to say anything to speak of about sense because I know that most of you are pretty familiar with the general concept. But what I'm going to do first is just explain the context, the sense context of what I'm going to say for the next 15 minutes. Because sense, as you all know, is based on the idea that aging is the progressive, lifelong accumulation of various types of molecular and cellular damage that are just side effects of normal metabolism, i.e. the normal functioning of the machine that we call the human body, and that eventually that damage gets to a level of abundance that is problematic and eventually insupportable by metabolism, so that we get sick and then we die. And therefore, the way to do something serious about aging is to actually find ways to repair these various types of damage periodically so that we keep the level of damage down below that threshold that causes the pathologies that we're so familiar with in old age. And that's all very well, but it would be nice to know whether it was actually true. I mean, in some sense you might think, well, it's sort of almost a truism that aging is like this, that it's the accumulation of damage, but it's perhaps a little bit premature to say that quite so categorically. Because that whole concept, even before we go into any details like, what the damage is, does make some interesting predictions that we might be able to look at already, and that might be actually falsifiable. So one of them relates to the question that I asked Michael at the end of his talk just now, which is with relation to the analysis of the physiological state of flies as they're getting older. And as Michael said, there's still not enough data on this, basically. It would be great to have a lot of data, not just in fruit flies, of course, but also in humans, longitudinal studies, i.e. studies of the same individual over time until the end of their life, to figure out whether things are going on that are progressive, that are accumulating, whether damage is accumulating, whether physiological function is declining throughout life in the individual organism, and whether that relates to the likelihood of death. Now, what Michael spoke about, and indeed what you've heard for most of this session, relates to a sort of proxy for that, which is the mortality rate. The distinction I'm making here is between the mortality rate and the mortality risk. So the mortality risk is the phrase I'm going to use to discuss the probability of a particular individual in a cohort or whatever actually dying at any particular time. And of course, you only see them die once, so you can't actually see that number until they die, and you don't see it then either. But you have a proxy for that, which is the mortality rate within a population, the proportion of a given population that die at a particular age, or to be more precise, the proportion that get to a particular age and then die before the next time increment, whether that be a day for flies or a year for humans. Okay, so it might be that the whole concept of sense, the whole accumulation of damage hypothesis for what aging is, could actually make some predictions that we could test by looking at distributions of mortality rate, which is more or less what you've heard today. And I want to make sure that you all understand that actually a lot of what you've been told today, both by Michael and actually by Steve, asks some big questions about whether that hypothesis could be true. It's pretty damned hard to see, if aging really is simply the accumulation of damage, how mortality rates could do anything other than mortality risks could do anything other than continuously increase until the end of the individual's life. In particular, really, it's pretty hard to see how the risk could do anything other than simply accelerate. In other words, rise at a progressively increasing rate throughout life until the individual dies. So we really need to know what that means for mortality rates. What we've heard from Michael and from Steve is that mortality rates don't seem to do that. We have this accelerating rise, specifically an exponential rise with age in the mortality rate through most of the life course, in other words, until most of the individuals in a given cohort are dead. And then we see this weird plateau thing, this weird leveling off that is very much not, well, it may initially be still an increase with age in the mortality rate, but certainly not an accelerating increase. So this is pretty damn strange, and it would be awfully nice to know whether it does, in fact, contradict the hypothesis that aging is all about the accumulation of damage. So I want to talk a little bit about the sparring that Michael and I have done actually over some years now, including in the published literature, and to explain why I think at this point we definitely need more data on this. So one thing that you've heard from Michael is that there is this enormously important relationship between mortality rate and age, which I've already alluded to, that is basically an exponential rate. It's called the Gompertz relationship because it was identified first by a British actuary named Benjamin Gompertz back in 1825, and it basically just says that if you look at the distribution of ages of death of a population of individuals and you plot them as mortality rate, in other words, as I said, the proportion of a set of individuals that reach a given age but do not reach the next time increment. And furthermore, if you plot that as a semi-log relationship with a log scale on the y-axis and a linear scale on the x-axis, then you get a straight line. That is what you get for most of the life course. I'm actually going to draw it. I'm going to use Paleolithic technology since it's, as we've heard, right? Okay, so I'll go over here. So you've got, basically, I don't know whether the camera is pointing here, but it'll do. You've basically got something which early on in life looks very different because there are things other than aging that are affecting mortality. But after a little while, you've basically got this straight line. If you draw, as I say, mortality rates on a semi-log scale. And then it tails off at the end. Now, it would tail off at the end on this sort of curve, even if you did have a straightforward exponential rise with age, basically because the time increments are finite. I won't go into the details of that. But it tails off a lot more dramatically than that, as we've heard from Michael. So there's definitely something funny going on, a plateauing going on, a real plateauing, not just a statistical artifact. And one way to explain that, which is, I guess, the most obvious way, is that each individual in this population whose mortality rate we are describing here is aging at an exponential rate. In other words, their individual risk of death is going up exponentially throughout most of their life. But then the relative minority of that population that are lucky enough to get somewhere up here start to age more slowly and eventually not to age at all. So, in other words, their risk of death per unit time does not rise. That's the simplistic, the obvious explanation. Thing is, though, there's another explanation, which is that all of the population are not the same. So the Gompertz relationship, as we've heard, is a simple mathematical relationship, and of course it's an exponential relationship which can be drawn as a straight line on a semi-log curve. That basically means that there are two parameters to it. So the parameters are often called A and alpha for reasons that escape me. And essentially, one of the parameters is the slope of this line, and the other parameter is the intercept, the place where this line, if you extrapolated it backwards to age 0, would actually hit the y-axis. And of course, those two parameters are both very different between different species. So in humans, pretty much all populations have a slope that you can describe as something called a mortality rate doubling time, and that doubling time is between 7 years and 8 years. Okay, in dogs or in mice, the doubling time is a lot shorter. And the same is true for the intercept. The parameters are just different. Now, why are they different between different species? Obviously, because different species have different genetic basis for how long they live. Now, if we then ask, well, okay, what does that tell us about a population within the same species, a population of individuals, we can see that both for genetic reasons and, of course, for epigenetic reasons, we're likely to see the same thing. That each individual, even if every individual is, in fact, aging exponentially, their risk of death is going up exponentially throughout their life until they die, nevertheless, the two parameters of that risk are going to be slightly different for different individuals. And the question then is, if we take that into account, what can we predict? Or, to put it a little bit more strictly, what can we see that we can't predict about what mortality rates would look like? But the short answer is, well, I've only got 5 minutes left. The short answer is that, that we will predict much more of a plateau than if we don't have that heterogeneity in those two parameters. The amount of plateau that we get depends on basically on the standard deviation of those two parameters, and it turns out that if you only have a heterogeneity in the intercept, then you definitely can't fit real data. But it turns out that if you have heterogeneity in the slope as well, which of course you would expect that you would in real populations, then you can get something that's very close to this, to what we see in real data. The published sparring that Michael and I had in the literature several years ago now related to a paper that Michael published which purported to show that in fact even if you have heterogeneity in the slope of the population, unless you do something very artificial with that heterogeneity rather than just having it normally distributed, you just can't fit Michael's own data. But basically, my response was that he'd done the statistics wrongly, essentially that he had indeed fitted the best possible Gompertz curve to the data and shown that it didn't fit very well, even if you put in this heterogeneity, but that actually you shouldn't be fitting Gompertz curves. You should be fitting something slightly different called a Gompertz-Makeham curve, which basically is a Gompertz curve plus a contribution, a non-zero contribution of age-independent mortality. And by age-independent, I don't mean this intercept down here. I mean actual risk of death that is the same however old you are. Risk from predation or starvation or hypothermia or whatever it might be. And I found when I threw that parameter in, which, well, actually I did it in a rather preliminary and quick and dirty way, but it was good enough for the purpose, that if you threw that in, then the conclusion that this sort of heterogeneity would not fit the data, which is what Michael had published, didn't work anymore. You could fit the data perfectly. Unfortunately, this has some big implications. One big implication it has is that if you have a lot of Makeham term, if you have a high age-independent risk of death, you're going to see an earlier plateau by the sort of calculations that Michael does than if you don't. When I say earlier, what I mean is a higher proportion of the individuals are going to be still alive at what Michael calls the break point, the point where this plateau begins. And therefore, my prediction, unfortunately, my rather pessimistic prediction, is that the only way that it's going to be possible to manipulate a population so that a higher proportion of the individuals are alive at the breakpoint, or conversely to say that the breakpoint happens when a higher proportion are still alive, is by simply increasing the age-independent risk of death, which is probably not what we want to do. That's a bit of a shame. However, what I want to point out is a couple of other things to show that this is by no means, that the case is very much not closed on any of this. First thing I want to notice, which Michael didn't quite have time to mention, is that in one of the seminal papers from 1992 that really started all of this, there was a finding, this is from the paper by Jim Carey, that actually we see a rather sharp decline in mortality rates at very old ages. And a lot of people worried about this. But I worried about it quite a lot because it turns out that you can't actually fit that data using this heterogeneity argument that I've given you, or at least only if you do something really rather artificial. And so there's definitely something more to be discovered here. If I now talk about Steve's remarks about the supercentenarians, the same sort of paradox has begun to emerge. We appear to be seeing a tailing off, a plateauing of mortality that's very similar to the sort of plateauing that we see in fruit flies. But as we've got more and more data on supercentenarians, it appears that things are doing more than just wobbling around randomly at the end of the survival curve of the very oldest old. My sense is that we still don't have the numbers to be sure that this is true, but I'm beginning to think that it is true, that we've got to understand that the curve at the end of life, if we draw it as a straightforward exponential curve rather than a semi-log curve, is doing this, and then tailing off, and then doing this again, and perhaps tailing off again. In other words, that we've got a very much more interesting pattern of mortality than we might have thought we had until just a few years ago. And I'd really love to see more work on that. So I really want to see a lot more of this done, a lot more experiments done in this area. I certainly want to know much more about the physiology of the fruit flies that Michael is looking at, and of course the physiology of supercentenarians. I also want to point out that everything I've said is about this plateauing, and that the product that geneticians have just brought out, Stem Cell 100, really doesn't have very much to do with this. It's more to do with, if you like, Michael Rose's first life, where the discovery of the general concept of of malleability of longevity. So it's all, you know, a rather different topic. But there's a lot more to find out. And I think just in my last word, I want to say, I want to draw attention to something that Greg said, or showed more precisely, which was the survival curves of flies treated with this stem cell 100 thing, which had this totally bizarre survival curve with this sort of, if you remember rightly, let me do it over here, something like this. Now, that's the sort of thing qualitatively that you see in any survival curve, but normally it looks more like this. Okay, it looks much more, but you get a tailing off, but it's a tailing off very much closer to when when almost all the flies are dead. If you plot this as a mortality curve rather than a survival curve, and once you've seen a few of these, you get pretty good at eyeballing them and understanding roughly what the mortality curve would look like looking at the survival curve or vice versa, then I can tell you that that's a pretty damn weird mortality curve. So there's definitely a lot more to be found out here, and I'm delighted that there is so much work going on in the area. I strongly support it, even though it may show that I'm completely talking nonsense with sense. And thank you very much.